Sedimentary rocks are fascinating because they witnessed the past history of the Earth. Their study should unveil mysteries about their formation and the history of living species. The principal features of sedimentary rocks include distinct stratas of relatively homogeneous material. Intermittent settling over very long periods of time figure among possible explanations of stratification. Internally, sedimentary rocks display microscale stratification or lamination of relatively coarse and fine particles. Because sedimentary rocks form from settling of particles underwater, it is instructive to study fundamental sedimentation patterns in the hydraulics laboratory. A mixture resulting from equal weights of coarse sands in black and fine sands in white is tested in the laboratory.
Consider the motion of a sphere rolling on a horizontal surface. The radius of the sphere is r, the mass is m, the angular velocity omega, and the translation velocity v is equal to omega times r. The moment of inertia of the sphere is equal to 2/5 of the product of the mass m and the square of the radius. The kinetic energy of the motion is given by the following formula. E is equal to 7/10 of the product of the mass times the square of the velocity. This formula shows that at a given velocity, the kinetic energy of a sphere increases with the mass. It shows that coarse particles have a higher kinetic energy than finer particles.
This example illustrates that rolling coarse particles have more kinetic energy than small particles. The mobility of coarse particles in front of obstacles or surface perturbation therefore increases.
Consider a homogeneous mixture of coarse particles in black and small particles in between. When we set this mixture into motion, the small particles which have a lower kinetic energy fall between the coarse particles and deposit on the bottom of the moving layer. The coarse particles with higher kinetic energy roll on top of the fine bed of fine particles.
Particle segregation occurs under lateral motion of a mixture. Coarse black particles roll on top of fine particles when they have the same specific gravity. Submerged particles under hydraulic shear stress also display the same particle segregation characteristics. The fundamental question about lamination is the following. Does nature produce repetitive segregation under a continuous supply of sediment? First, the submerged conditions are examined. The turbulent fluid motion surrounding the particles led scientists to believe that lamination was caused by periodic cycles of turbulence. When the same experiment is carried out in the air, the settling cone displays all the features of lamination through repetitive segregation. Moreover, the laminae thickness increases with the feeding rate of the sediment mixture. It should be noted that laminae form in the direction of motion, here at an angle exceeding 30 degrees. Given the absolute vacuum is at minus 29.92 inches of mercury, the hypothesis of turbulence is tested near complete vacuum at minus 22 inches of mercury. Lamination develops without the presence of a surrounding fluid. Lamination therefore depends on the mechanical interaction between particles of different sizes, different shapes, and different densities. Under submerged conditions, lamination also occurs during gradual aggradation of the bed under plain bed conditions. Here's the same lamination sequence in accelerated motion. Large-scale experiments on stratification were carried out at the Hydraulics Laboratory of the Colorado State University Engineering Research Center. For the experiments, a 4-foot wide flume measuring 60 foot long recirculates 1,000 cubic feet of water and 8 tons of a sand mixture. This flume provides a continuous supply of coarse and fine sand particles under steady discharge conditions.
Consider a typical delta sketched on the board. At the initial time t1, the delta is comprised of 3 parts: the top set, the foreset, and the bottom set slope at initial time t1. Over time, the coarse particles rolling on the bed slide down the foreset slope of the delta and accumulate as the delta progresses in the downstream direction. Finer particles rolling on the bed settle and form a layer of primarily fine particles. The particles in suspension are carried through and deposit on the bottom set slope of the delta. After a certain time interval, we get a second bed profile at time t2. The sediments accumulated on the bed from time t1 to t2 define what is called a layer of sediment. A layer of sediment is the accumulation of sediment between the initial time t1 and the subsequent time t2.
This typical delta gradually progresses in the downstream direction A close look at the top set slope in slow motion clearly shows a laminated deposit of finer particles. The thickness of the top set deposit decreases in the downstream direction as the foreset slope of the delta is approached.
Over a long period of time, the accumulation of sediments displays clear stratification, with fine particles on top, coarse particles in the middle, and fine particles on the bottom. It is important to understand that the chronology of the formation of the deposits depends on the layers and not on the strata.
Isochrones correspond to the interface between successive layers, not strata. The thickness of strata is determined by the changes in sediment transport that occur in non-uniform flow.
Let's now consider two particles in the delta. Particle A in the upper strata and particle B in the lower strata. Particle A deposited at a time T1 before particle B. Particle B in the lower strata therefore deposited after particle A in the upper strata.
Increasing the flow depth while keeping the discharge and the supply of sediment unchanged results in more complex sedimentary features. Substantial deposits accumulate with features including deltas, dunes, and ripples at various stages of development. A dried delta, viewed from the flume sidewalls, displays clear stratification characteristics in terms of superposition of deposits with similar particle size distribution. A cross-section is cut through the delta to examine the primary features of deposits of sediment mixtures carried out under steady flow and a continuous sediment supply. The cross-section displays a clear superposition of strata of fine particles in white and coarse particles in black with clear lamination. Looking at the cross-section of superposed strata, it is tempting to conclude that the strata correspond to successive sedimentary layers, that they result from discontinuous sedimentary periods, that each strata is younger than the one underneath it and older than the one above it, and that all points of the same strata have the same age.
The stratification experiment invalidates these hypotheses because these strata are not identical to successive layers. Moreover, clear stratification is observed under a continuous supply of heterogeneous sand particles.
Why is this important? Well, quite simply, because strata have been used to date sedimentary rocks and the fossils in them for over 100 years. And now, for the first time ever, there is experimental proof to show how strata form. And it is quite obvious that strata cannot be used to date either fossils or rocks. In fact, the fossils in the bottom strata could be younger than the fossils in the top strata.
Here you see some sea creatures which live at different ecological levels. A heavy influx of sediment arrives and they all get buried. Eventually, if no air gets to them, they could turn into fossils. Obviously, those buried in the top strata are the same age as those in the bottom strata, as they were buried in the same layer of sediment. Then another heavy layer of sediment arrives, and more sea creatures are trapped. But what is more important is the ones at the top of the previous layer were buried before the one in the bottom of the last layer. So the one at the top here is older than the one at the bottom.
Let the director of the research program explain.
La théorie de l'évolution se base sur la
Evolution
croyance
theory is based upon the belief that a succession of fossil species in a scale of geological time demonstrates that evolutionary progress has taken place. As we have seen, however, and as we have shown in the laboratory, layers of incoming sediment have been wrongly identified as being strata. The scale of geological time and the chronological succession of fossils have been calculated on this mistaken belief that strata are successive layers of sediment. A single layer of sediment can sort itself out into parts of many strata. So the position of fossils in the rock strata could simply indicate the ecological zones of marine species. Stratigraphy, as interpreted by observable facts and experimental data, challenges the geological timescale and therefore evolution theory.